Hey, good evening, everybody. I'm sorry for all the delays. I can't get the thing we're supposed to display up here to display properly. So I might have to go back and forth to look at the problem sets. Today, we mostly want to review for the exam coming up next time. So on Monday, we have exam 1, we said last time, on chapter 9. Just through 9.8. I do want to mention 9.9 tonight. Maybe I'll assign a couple of problems out of that. Were there any questions out of 9.8? I guess I should ask on the homework. Anything that was difficult? Do the practice problems on D2L if you haven't already. Send me an email or get in my office hours and talk to me if you have any difficulties. Those will be the main source for the exam, but I'll ask anything that's similar to the homework problems. There may be some problems in the exam. All right, well, I just want to make a couple of closing comments on these series. Note, this is really 9.9 at this point. For power series, within their radii of convergence, another thing you can do besides add series or multiply series by a number and this sort of thing is take their derivative or integral. The derivative, for instance, exists and is within the same radius for a function f of x with a power series Cn x minus x0 to the n, sum n equals 0 to infinity. So here's a general power series. It's got an infinite list of constant C0, C1, C2, and on forever. The derivative is just taken term by term. What could be easier than that if you had to memorize what to do, right? You take the sum up to infinity of Cn, and what's the derivative of this nth term? The derivative of x minus x0 to the n is n times x minus x0 to the n minus 1. All right? And now you can say truly that runs from n equals 0 to infinity. However, if you really think about it, the C0 term times x minus x0 to the n means just C0 times 1. And so the first term in here for n equals 0 is a constant. And when you take its derivative at 0, now that's reflected here, you've got 0 times something. Nonetheless, typically we start the series at n equals 1 because that first term comes out, constant term comes out to be 0 here. So there's how you can take the derivative of an infinite series. You just take the derivative term by term, right?
Professor, we can't really see the board. Can you point the camera down?
Oh, okay. I'm looking at the monitor here. It's showing the whole board. That's strange. Okay.
Yeah, we see the monitor, but we don't actually see the board.
Oh, okay. You're seeing the monitor of the board. I'm sorry. I had all sorts of problems getting this working today. Let's see if we can. Oops. Yeah, I'm sorry. Sheesh. Okay.
Thank you.
See if I can zoom that in a little bit too. Maybe that's better. So here's what you do, you take the derivative term by term. Here's a nice easy example just to illustrate that it really works. Suppose I wanted the power series for sine 2x. What do you think the power series is for that based on what we did last time? That was not like one of them we memorized. We memorized the power series for sine x. I wonder what the power series for sine 2x is. I can calculate it as the Maclaurin series by taking the derivative, putting in 0, taking the second derivative, putting in 0, and constructing all those derivatives, or I can figure it out from the power series for sine x, right? If I rewrite this and say this is actually sine u, or I let u equal 2x, I can figure it out immediately without having to go compute all those derivatives, right? Remember the power series for sine u was u minus u cubed over 3 factorial plus u to the 5th over 5 factorial minus u to the 7th over 7 factorial, and so on. And now if you just put u equal 2x, you find the power series for sine 2x without having to calculate all those derivatives. Now this is u, which is 2x, minus u cubed, which is 2 cubed x cubed, all over 3 factorial, plus u to the 5th, which is 2 to the 5th x to the 5th, over 5 factorial, minus so on and so forth, on forever. There's the formula for sine 2x, and now what's its derivative? Derivative of sine 2x is cosine 2x, right? Sine 2x derivative, we could just take that derivative term by term is what I'm saying. I can take the derivative of 2x and get 2. I can take the derivative of minus 2x cubed, minus 2 cubed x cubed over 3 factorial, and that derivative is 2 cubed times 3x squared over 3 factorial. And then the derivative of this one, 2 to the 5th times 5x to the 4th over 5 factorial, and so on and so forth. And you can see the pattern evolving. And so the derivative of sine 2x is this. It's 2 minus, and now I can cancel this 3 with up here, right? 3 factorial is 3 times 2 times 1, which is 3 times 2 factorial. So I can cancel the 3 here with part of this and call this 2 cubed x squared over 2 factorial. Let's call it that. And then here, 5 factorial is 5 times 4 factorial. So I cancel this 5 for this one and call this 2 to the 5th x to the 4th over 4 factorial. And then minus 2 to the 6th x to the 5th, oops, to the 7th x to the 6th over 6 factorial, and plus so on and so forth. I just take the derivative term by term like that. And now what you can do is this, factor out a 2 and multiply as brackets as 1 minus 2 squared x squared over 2 factorial. So the theorem says that this is now the power series for the derivative of sine 2x. And what we find out if we look at this, wait a minute, this is 2 times 1 minus 2 squared over 2 factorial plus u to the 4th over 4 factorial minus dot 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 where u equals 2x again. That's the series for cosine, if you remember from last time. So we actually get that this is 2 cosine u or 2 cosine 2x. As expected, derivative sine 2x by the chain rule is 2 cosine 2x. Here's just a verification that derivative term by term works for this example. Without proving the theorem, I can at least show you an example works, right? All right, so that's derivatives, and then similarly, the integration works. Integration is term by term, and then you have to add an arbitrary constant. So if I have this thing, what's the integral of the series x to the k over k factorial, k equals 0 to infinity. Does that series look familiar? This was the series for e to the x, right? If I'm going to do it, I did it taking it out of sigma notation in here. I'll do it in sigma notation this time. You can do it either way. Also, this is the integral term by term sum k equals 0. We'll integrate it term by term. It's sum k equals 0 to infinity. Integral x to the k over k factorial dx. That, in other words, you take the integration term by term, gives us, well, let's see, sum k equals 0 to infinity, x to the k plus 1 over k plus 1 is the integral of x to the k, and then the constant 1 over k factorial just stays there, right? And then I have a plus c. And you think about that for a second. What you've got, if you make a substitution here, that n equal k plus 1, and let's see. And so k equals n minus 1. Then you can rewrite this sum when k equals 0, n equals 0 plus 1 is 1. So n is going to start at 1. This is re-indexing the series. You can change this. After all, this is just a dummy index, right? K. If you write this out, like if you write out this series, all this means is to put in k equals 0 and get 1, put in k equals 1 and get x, put in k equals 2 and get x squared over 2 factorial. K is just an index that knocks these off. You can change it to anything you want. Right? So I'm going to re-index this and let n equal k plus 1, in which case I get n running from 1 to infinity. That's k equals 0, n is 0 plus 1 is 1. And now x to the k plus 1 becomes x to the n over k plus 1 is n. K is n minus 1. And now wait a minute, n, oops, this is n here. k plus 1 is n. N times n minus 1 factorial is just n factorial, so this is sum n equals 1 to infinity, x to the n over n factorial, and then there's a plus c, I forgot to put in here, plus c. And what's that? This is the power series for e to the x again, except you're missing the first term. You can fix that by putting in part of the constant in here and say, well, this is the sum n equals 0 to infinity, x to the n over n factorial, plus an arbitrary constant c1, where c1 equals c0 minus 1. Because what I did was I added 1 in the series by putting in the n equals 0 term. Right, it's 1 over 1 factorial, 1 over 0 factorial, and 0 factorial is 1. And so if I make this arbitrary constant equal to this arbitrary constant plus 1, now I observe that what I have is e to the x plus an arbitrary constant. As expected, the integral of e to the x is e to the x plus a constant. I see this verifies term by term integration. This time I did it in the sigma notation, but you can do it either way.
Are there times when it's easy to take a derivative or integral using this process? Or is this just kind of verifying?
What happens in practice is, if it's a standard function like sine or cosine or that kind of thing like we did here, it's usually easier just to use the formula you memorized. But if you get a series that represents some other function, the solution to some physical problem that's not in terms of standard functions, you have no other choice, and then you do this. So what will happen is if you take differential equations class, you'll solve a differential equation in terms of a power series, get some function nobody's ever heard of before, but you can find its derivative term by term. I think that's all I'll say on that chapter then. I'll assign some problems for you to look at, but they're not for this test. Out of 9.9, just to complete this series, you might look at 1, 3, and 7. Not for this test. Rest of the time tonight, let's take a look at some review problems that you're interested in. Any particular problems in mind? I believe this is the first problem on the review sheet. Looks like that. And I asked you on this one, and I'm going to ask some of these problems. I like to do this just like that very first problem you see on the practice test. Is this absolutely convergent, meaning the series of corresponding absolute values converges? In which case it has a nice property that you can rearrange an infinite number of terms without affecting the value of the sum. Or is it convergent but not absolutely, in which case we call it conditionally convergent. That means the series converges, but if you take their absolute values, that new series doesn't converge. Or the other case that can happen is it might just diverge. It might not approach any number as you take the sum. How about this one? One of the things you want to have for this test is an intuition. What should that be? And then once you have the intuition, usually you can figure a way to improvement. And I'll give you a big hint, at the end of section, I think it's 9.8, at the end of one of the sections there's a big list of all the convergence tests that you have. And so when I ask you this question on test, you can just look through all of them. No. Since it's an open book test, and I should reiterate that. It's open book, open notes by email. You don't have to get on WebEx. Just get on your email, open book, open notes, open computer, just no help from people. I'll give it to you at the beginning of class, the usual time, 6 o'clock, you return it by 7:15. If you have some technical difficulty, maybe it can be fixed. If you can't print it out, if you just read it, you can write it on the blank paper, number the problems, and just photograph it on your phone and email it to me. However you want to send it back. But just like the extra credit problem. Open book, open notes, and computer, but no help from people. So what you do when you see this is you can go look at that big list in your book and say, this looks like a good test, and try it. But if you don't practice these beforehand, you won't have the intuition to be able to use that list. It'll take you too long, you won't finish the test. So you want to look at this and say, what test should I use? I'm going to give you a hint. This one, I just look at it and it looks divergent to me. Why is that? It's because if I forget the ln of k, this looks like 1 over k plus 2. What does that look like? Well, it looks bigger, because ln is a growing function, right? Looks bigger than the series 1 over k plus 2. I try and compare this with some simple series that I know converges or not. Particularly p series are useful. But what is this? If you think about it, you put in k equals 0 and you get 1/2. Put in k equals 1, you get a third, then you get a fourth. What series is that? That looks just like the harmonic series except for one term, right? Any finite number of terms in front don't affect convergence. If you take out any finite number of terms anywhere, it does not affect convergence. So this one adds up to infinity because the harmonic series does. This is harmonic series, 1 plus 1/2 plus 1/3 plus 1/4, less its first term. Well, I look at this and I say, this one I know diverges. This one, ln of k times each term, bigger than one term, is going to be bigger. So I use that as a basis to show that this is actually divergent. So that's what you do. You can do a comparison test. For instance, think something, the terms are bigger than something you know converges. That's a case for the comparison test. So the comparison test, you simply base it on that intuition and say, ln of k over k plus 2 is bigger than 1 over k plus 2. All right, at least for not the first term. Oh, you know what? I think this is ln of k plus 1 maybe, because I can't take ln at 0. Let's try that one. Maybe there's a typo on it. Let's put ln of k plus 1. If I put in k equals 0, then this is 0, and that's actually smaller. So the first term is actually smaller, but beginning with 2, I get ln of 2, that's bigger than 1. And so this is bigger than this for k large enough, or for at least for k equals after the first term. So it's event, maybe I should just put that word eventually. I think it's just one term that doesn't hold. Eventually meaning after a finite number of terms it holds. So this is true eventually, and sum 1 over k plus 2, k equals 0 to infinity, is infinity. It's the harmonic series without the first term. So it sums to infinity if the harmonic series does. Therefore, sum natural log of k over k plus 2 diverges also. K plus 1. By the comparison test. Pull the next one down here. Oh, I see. What I did, I started at k equals 1. That's what the actual problem is. It's the same result. Okay, 3 over 2k to the 1.5 minus 1. Suppose I have this one. This is 1p. K equals 1. How about that one? This one you'd like to use a comparison test too. For large k, you think of this, that the kth term here is approximately 3 over 2 times k to the 1.5, because for k large, this minus 1 just is way back in the digits, and the bottom is approximately 2k to the 1.5. So you think like that. And so what if this was the sum of these? Would that converge or diverge? Well, this would be 3/2 times the p series with p equals 1.5, which is convergent. So this time I'm going to expect it to converge because I can compare it with a p series with p equals 1.5. So now I'd like to use the comparison test again maybe, but because of this minus 1, it's kind of awkward. Instead, I'm going to use the limit comparison test. Limit comparison is easier when you have some awkward terms and you're just looking at the dominant contribution like this. Limit comparison, what I can do is compare a series, this one, sum k equals 1 to infinity. Let's just take 1 over k to the 1.5. We could also use 3 over 2 times k to the 1.5. But let's just use that one. And then you compute rho is the limit as k goes to infinity of the ratio of terms of this one to this one, or the other way around, it doesn't matter. So what the kth term of this one, 1 over k to the 1.5, over the kth term of this one, 3 over twice k to the 1.5 minus 1. And what is that limit? Well, calculus 1, right? Limit k goes to infinity, top times bottom over middle times middle, and we can take the 3/2, 1 over 3/2 out is 2/3. 1 over 3/2, and I'll take 2k to the 1.5 minus 1 over k to the 1.5 is left. Top times bottom over middle times middle, pull the 2/3 down. Oh, maybe I better not do this. It's making, sorry, we'll just write it like that. There we go. So top times bottom over middle times middle. Let's write it like that. And now what's this limit? You take the quotient of the dominant term, right? The 1 doesn't contribute, but the quotient of this thing is then 2/3 by calculus 1. Saying it's the quotient of dominant terms. And when this is positive and not infinity, greater than 0, not infinity, that means these both converge or both diverge. Which is it? So this one is a p series with p equal 1.5. Remember, if p is bigger than 1, then it converges. They have to both converge or diverge by the limit comparison test. It's the limit of the quotient of corresponding terms in a series of positive terms like this is a positive number, not infinity, and they both do the same thing. So these both converge. What we've established is the original series converges. So you look at it and say, it looks like this series, that looks like 3/2 times a p series. And there's the details of it. I don't expect a lot of details, but just something like this. It says compute row and say, therefore, since this one converges, that one. I was going to print out a sheet for this tonight, and I guess I should have, because I never expect to have to walk back here to look these up. 3 to the 2k over 3k factorial. That's the next one. How about this one? Same question. Does it converge absolutely, converge conditionally, or diverge? And I should have put on there whether it converges conditionally or absolutely. What do I know? Well, this is a series of positive terms. Whenever you use one of these tests for series of positive terms and it converges, well, the series of absolute values is the same series. These both converge. Since terms are positive, I should have said, convergence is equivalent to absolute convergence. I'm going to stand in front of the letter there. So that's that one. The first thing diverges, this one converges absolutely. How about this one? These things, remember when you see powers, kth powers, and kth factorials, you think of the ratio test, right? A ratio test is this one. When I see factorials and powers. Some or both of them. Sometimes you can have other stuff in there. That's why these are good for the Maclaurin series and Taylor series. Is that those have factorials in them by their definition and powers in them by their definition. So it's a very good test for those. All right, the ratio test on this one says you compute rho equals the limit of the quotient of successive terms. K goes to infinity of the k plus first term over the kth term. So the kth term is just 3 to the 2k over 2k factorial. Oops. And how do you find the k plus first term? You just put parentheses wherever you see k there and put in k plus 1. So I get 3 to the 2k plus 1 over twice k plus 1 factorial. So there's a ratio test. It's the, if you call this uk the kth term, you're taking the quotient of uk plus 1 over uk. That's the ratio test. More familiar form. Well, now how do we deal with this? We take top times bottom over middle times middle. We'll take limit k goes to infinity of 3 to the 2k plus 2 if I multiply that out, times bottom is 2k factorial over middle times middle. 3 to the 2k times 2k plus 2 factorial. If I multiply that out. There it is. What's that limit? Well, in these, you can cancel some things. You can rewrite this as limit, well, let's do this. 3 to the 2k plus 2, you cancel the 3 to the 2k with the 3 to the 2k, you're just left with 3 squares. 3 squared. And then over here, you've got 2k factorial. 2k plus 2 factorial can be written as 2k plus 2, 2k plus 1, times the numbers 1 through 2k, right? Well, that's 2k factorial. This means the numbers 1 through 2k plus 2 all multiplied, so that's this, right? Now you can cancel the 2k factorial with the 2k factorial, and what you've got is what you've got is this now. The 3 squared is a constant, so you can rewrite it as 3 squared, limit as k goes to infinity, 1 over 2k plus 2, 2k plus 1. Well, that's an easy calculus 1 problem, right? The bottom is going to infinity. Top is just staying at 1, so the limit is 0. This time you can allow 0. For the limit comparison test, you want some positive number, not infinity. But for the ratio test, what you want is anything less than 1, including 0. When rho is less than 1, you say, therefore, this converges. Now the question is, once it converges, is it absolute convergence or conditional convergence? Once again, if you think about it, these are all positive terms, right? 3 to the power is always positive, and the factorial is always positive. Since the terms are always positive, it converges. Absolute convergence is equivalent to convergence. It converges absolutely. So it converges and absolutely since terms are positive already. Any particular problems we should look at, or is this good? I gave you a hint on some of these also. Here's another one. Sum minus 1 to the k over k plus 1. K running from 1 or 0 to it doesn't matter. How about that one? Does that one converge or diverge? Converge absolutely, converge conditionally, or diverge? This one, if you look at it, you notice that terms here, the absolute value are getting closer and closer to 1, right? And so when you k over k plus 1 as k goes to infinity approaches 1. So this looks like it's going to oscillate closer and closer between plus 1 minus 1, plus 1 minus 1. So I expect this one to diverge. How can I show it diverges? This is where it's nice to have that list. You can use the divergence test. You can say since, if we call this the term uk, the kth term, since limit as k goes to infinity of the kth term minus 1 to the k over k plus 1 is what? Well, k over k plus 1, the limit would be 1, and with times minus 1 to the k, it just doesn't exist. The series diverges. by the divergence test. The divergence test says if a series converges, then the limit of the kth term is zero. The limit of the kth term isn't zero, it doesn't converge. So use the head, I think it's really useful, but you don't have to use it. You can use your own method. Prefer another one. All right, here's another one. This is not on the list there, but I'll add this one. Suppose I have sum k equals 1 to infinity. Natural log of k times minus 1 to the k minus 1 to the k over natural log of k. K equals 2 to. How about that? Does that converge absolutely, converge conditionally, or diverge? Once again, you think, what if I looked at the terms and if you notice in here, the terms alternate in sign, right? Plus 1, minus 1, plus 1, minus 1, because of this minus 1 to the k. When k equals 2, you get positive 1 on top. K equals 3, you get negative 1 on top. The bottom is always positive, right? So this is positive, and this alternates sign, plus and minus. So you think maybe I should use the alternating series test. Alternating series test is nice. All you have to do is this. Show that the terms alternate in sign. You look at the absolute values of the terms. AK, the absolute value of the kth term, is 1 over ln k. Leave off the minus 1. And tells you that AK plus 1 is 1 over ln k plus 1 is actually smaller than 1 over ln k. Why? Easy, I don't expect you to prove it or something, but natural log of k goes like this. It's increasing. You can show it by showing its derivative. It's positive, for instance. But y equals ln k is an increasing function with positive value for k bigger than 1, right? K and y equals ln k. Since the denominator is positive and increasing, ln k plus 1 is bigger than ln k, right? This is the bigger of the two denominators. If the denominator is bigger for positive quotients, then the quotient is less, right? So this is less than that, which is ak. So for alternating series, what you want to do to show convergence is you check the absolute values of the terms. I think ak is absolute value of the k term are decreasing, and their limit is 0. That's the other part we need. We take the limit as k goes to infinity of the absolute value of the kth term, 1 over ln k, all ak. Well, ln k, you remember, goes to infinity as k goes to infinity. And so this one's going to 1, and that one's going to infinity. The limit is 0. What that proves then, by the alternating series test, is this actually converges. Converges by alternating series test. This is an incredible series to me, because logarithm goes so slow. Suppose you took 10 to the 100th term. You took a Google term, right? 10 to the 100th is a Google. Means 1 followed by 100 series. If I added up 10 to the 100, that means way, way worse the number of atoms in the known universe. How big would ln of k be? Well, it's not much bigger than 100x. So you're still getting, but nonetheless, ln of k does go to infinity, even though it goes very slowly. Logarithm is a very slow growing function. Nonetheless, even though these quotients get small really slowly, if you add enough of them, you find out that actually this does converge. But you can have your computer working a long time before you get out of that. But that's the proof. You just do the alternating series test. When you see this -1 of the k, that's the hint. So try to show that the k plus 1 term is eventually less than the kth term, and that the limit of the kth term is 0, and that's it for an alternating series. It converges. However, that's not everything I want. I want to know, does it converge absolutely or just conditionally? That was the question.
The -1 is a conditional.
Yeah, this time it's not all positive terms, so I can't say it automatically converges absolutely. It's not positive terms. So I'm going to have to do is check the terms separate. Check absolute convergence separately. Now, the series of absolute values, you just take away the -1 of the k. That's what you're saying. That corresponds to this sum k equals 2 to infinity, 1 over ln k. You just take away the -1 of the k. Does that converge or diverge? So this is sort of two problems in this one. This one we diverges. How do we know? Easy way is to say, well, it diverges by the comparison test. With the sum k equals 2 to infinity of 1 over k. ln of k is less than k. The denominator is less on this one than on this one. So this one has larger terms, and this one goes to infinity. A series of larger terms also has a series of larger terms. 1 over ln k is bigger than 1 over k. This one also diverges to infinity. Now what we've shown by the alternating series test is actually does converge. It just takes a long, long time. But the series of absolute values diverges. Therefore, we have conditional convergence. Write that down. The series converges by the alternating series test, but the series of absolute values diverges. Okay. Here's the last series we'll do here. If you want to pick another one for me. How about this one? Is this absolutely convergent, conditionally convergent, or divergent? Again, what you try and do is look at a similar series. Say, for k large, these terms look about like 2 over fifth root of k cubed. We can just leave off the plus 1 since it's dwarfed by k cubed. If I just had that series, would it converge or diverge? Well, you can, since this would be approximately, except 2 times a p series with k equals 5/3, we expect it to converge. Let's rewrite it like this. Let's pull the 2 out here and take sum, and so you pull a constant out, k equals 1 to infinity. And let's rewrite this in this way. 1 over k cubed plus 1 to the 1/5. No, let's not do that. Since we've got this comparison again here, let's say once again, this by limit comparison, we say that asymptotically these look like this. We can compute rho is the limit of this series to this one. Here's the limit comparison test, limit of the k term in a series with those terms to this one. And now the 2's cancel, and we just get limit as k goes to infinity of top times bottom over middle times middle is k, fifth root of k cubed plus 1 over fifth root of k cubed. You can write that as a single quotient. It's limit k goes to infinity of the fifth root of k cubed plus 1 over k cubed. And now you remember that for a continuous function from calculus 1, you can pull the limit inside the root, provided that limit turns out to exist, or if it's infinity. So we can write this now as the fifth root, limit k goes to infinity, k cubed plus 1 over k cubed. Well, that's easy, right? Quotient of polynomials that approaches the dominant term. This one is equal to 1 over 1 is 1. Quotient of dominant terms. And so this is one. Rho equals 1 says that these series with this terms and this terms either both converge or both diverge. So since the other series, sum 2 over fifth root of k without the 1, k cubed without the 1, is 2 times a p series with p equals 5/3 is bigger than 1, converges, so does our series by the limit comparison test. There's that one. Finally, let's do this example. So we have sum k equals 0 to infinity, and put a harder root in here. 2k plus 1 over 3k plus 2, 1 over kth power, or the kth power. How about that one? Oh, by the way, that shows the series converges. Does it converge absolutely? Terms are all positive, so the series of absolute values is the same. So we say convergence is absolute, since the series already has positive terms. And how about this one? One last reminder, when you see that every term is a kth power or a 2 kth power, a 3 kth power, something like that, the root test is a possibility. Now we'll take the root test as we take the limit as k goes to infinity of the kth root of the kth term. And if that's less than 1, it converges. If that's greater than 1, it diverges. Well, this is why it's good for kth powers in here, is it undoes the kth power. And you have limit k goes to infinity of 2k plus 1 over 3k plus 2 is, both in dominant terms, 2/3. Right? Since this is less than 1, we get convergence by the root test. Since the terms are already positive, when it converges absolutely. And then we can always have an example like this. Suppose I had sum k equals 1 to infinity, 1 over k squared plus 1. How about that one? There's a lot of ways to establish this one. One way is to do a comparison test with the series 1 over k squared, right? Because this looks like 1 over k squared for k large. That tells you it converges like a p-series with p equals 2. And you could use the limit comparison test. It'll be a nice test. So we'll say limit comparison works. Using comparison with this series, what's another one you can do just to do a different one? Lots of times, lots of tests work. Ratio test might not, because I think the ratio of successive terms would still be k squared to k squared given 1. It would be undetermined. But the one we haven't mentioned here is this one. Since the integral from this value to infinity of the corresponding continuous function, 1 over x squared plus 1, but this is a decreasing function, decreasing positive function. We can evaluate this as the arctangent, right? Remember, 1 over x squared plus 1 is the derivative of arctangent. Goes from 1 to infinity. Arctangent at infinity is pi over 2, right, from this graph that we have of it, if you like. Here's y equals arctangent x. I mentioned this one earlier this semester. The limit of arctangent x as x goes to infinity is pi over 2 since it approaches the asymptote here. And then arctangent of 1, well, you're saying what angle has tangent equal to 1, it's pi over 4, right? So it's arctangent infinity minus arctangent of 1. This is a finite number. When the corresponding integral is convergent, so is the series. So therefore, sum 1 over k squared plus the integral is convergent, therefore the sum is also convergent by the integral test. A lot of tests, huh? Series are positive terms, so it's absolute convergence. If they're not positive terms, then you have to take the series of absolute values and do a separate problem and save the convergence like we did for that alternating series. All right, so that's all I wanted to do on those. I think it's a real good summary of these things. There are two cases where I want you to be able to actually evaluate the sum. All these things we've been doing is, does it converge? Does it converge absolutely? What if I actually calculate a sum? Evaluate exactly the sum, k running from 1 to infinity of 3 over 2 to the k plus 1 over k times k plus 1. How about that one? This is as hard as you can get for actually evaluating it. Yeah, it is. Here's what I'm going to tell you to really narrow this down. We only learned how to evaluate two kinds of sums exactly, where you find out what they converge to. It's a geometric series or a telescoping series. So if I give you one where I say evaluate the sum, it's going to be geometric or telescoping, or like this one, a combination of the two. What you say is, when this series is convergent, the sum of the sums is the sum of the sums theorem applies. You take sum k equals 1 to infinity, 3 over 2 to the k, plus sum k equals 1 to infinity, 1 over k times k plus 1. Right? Furthermore, you can pull a constant out. So I'll pull this constant out like this. Make it look a little easier. What kind of series is this? If you write these out term by term, the first term is a half, right? 1 over 2 to the first. The next one is a 4. The next one's an 8. You can probably see what the sums do already, but to prove it, you can say this is a geometric series because each term is multiplied by a half. Remember, if you go k equals 0 to infinity, you know the sum immediately. It's a geometric series. A over 1 minus r is the sum. Maybe we should re-index it and do it that way if you want. But this is a geometric series because each term is 1/2 times its predecessor. And the first term is A. So this is A is the first term. R is the multiplier. So the sum of this series is A 1/2 over 1 minus R 1/2. That's this one. Then we have to do the other one. But it's 3 times a half is 1. And you can see here, a half, a fourth, an eighth, a 16th adds up to 1 also. All right. How about this one? What do I do with this one? The trick for this one is you can rewrite it as a telescoping series. By partial fractions, you can say this is actually equal to 1/2 over k minus 1/2 over k plus 1. You can use your calculator to do that if you want, or you can do it by hand. I don't care. Let's see. not a half, it's 1, sorry. Yeah, 1 over k minus 1 over k plus. So the second one, what I do is I use partial fractions to rewrite it as 1 over k minus 1 over k plus 1. K running from 1 to infinity. Now to evaluate this series, I look at it term by term and I say when k equals 1, this is 1 minus a half. When k equals 2, this is a half minus a third. When k equals 3, it's a third minus a fourth, and so on. All the way, if I take the kth term, the nth term, I take the sum of the first n terms in this series, it ends at 1 over n minus 1 over n plus 1. So there's the sum of the first n terms in this series. And now you notice that minus a half cancels plus a half, minus a third cancels plus a third, minus a fourth cancels something here, 1 over n cancels something in here, and you're left with the sum of the first n terms is 1 minus 1 over n plus 1. So this telescoping series. You see this, write it by partial fractions like this. Calculate the sum of the first n terms. So what's the sum of this series? The sum of this series, if I write S for the sum, is the limit as n goes to infinity of the nth partial sum. That's the way the sum of series are defined, right? So the limit of the nth partial sum. So it's the limit of Sn, by definition. It's the limit as n goes to infinity of 1 minus 1 over n plus 1. Well, this is an easy calculus 1 problem because this goes to 0, 1 over bigger and bigger numbers. The limit is 1. So the limit of this series is 1. The limit of this series is 3. This thing, if you add up enough terms, adds up to 4. How about that? All right. I'm going to look at number 6 here, or 7. There's a bunch of them at the end we haven't got to yet. Let's try and approximate e to the x over 2 by a Maclaurin series. Two, I forgot how many decimal places accuracy was. Minus 0.1 to 0.1. 3 decimal place accuracy. And the idea is if I put in any x between minus 0.1 and plus 0.1, I want to get at least 3-digit accuracy. How can I get that? Well, we can compute all the series. The Maclaurin series means take the Taylor series at x equals 0, so we compute f of 0 with this f of x is e to the 0 is 1. What's f prime of 0? Well, let's write the function down. F of x is e to the x over 2. F prime of x is 1/2 e to the x over 2. That's by the derivative. E to the kx is k e to the kx. That's The second derivative is the derivative of this one. You keep the 1/2, and the derivative e to the 1/2 x is 1/2 e to the half x. So now I got 1 over 2 squared e to the x over 2. And I keep going, and I notice that f of 0 is 1 by plugging in 0 here. F prime of 0 is 1/2 times e to the 0 is 1/2. F double prime of 0 is 1/4. E to the 0 is 1/4, and so on. So the Maclaurin series I can write down immediately. I can calculate it by just plugging u equals, taking the series for e to the u and plugging in what u equals 1/2 x. But I'm doing this because I'm going to say we want the remainder with Rn of x, but the difference between the actual function, e to the x over 2, and Pn of x is approximation by the n, first n terms in the Maclaurin series. I said Maclaurin series, I should have said Maclaurin polynomial. Not taking the whole series, that would be exactly this. Maclaurin polynomial through n terms. What is this? We want this less than, for 3 decimal places, we want it less than 0.5 times 10 to the minus 4. That says whatever you write down here with a bunch of digits, we want less than or equal to 5 in this next spot, so these first 3 decimal places are accurate. All right, so you want less than 0.5 times 10 minus 4 is the definition of 3 decimal place accuracy. But we have a theorem that says this remainder is less than or equal to m over n plus 1 factorial, absolute value of x minus x0 to the n plus 1. This is the remainder theorem. The error is at most this big. That's I should have said taking absolute value here. Absolute value, this is absolute value, this is less than that. So if we can make this less than 0.5 times 10 to the minus 4, then it will follow that this is also using the remainder theorem, where m is the maximum n plus first derivative. Overall c between minus 0.1 and 0.1, the interval we're interested in. But what's the maximum? What is the nth derivative of c? This is an increasing function. This is less. You get the largest value by putting in the right endpoint, 0.1. So this is fn plus 1 at 0.1 gives the largest value. And this is 1 over, looking at here, the nth derivative is 1 over 2 to the n, e to the x over 2. So at 0.1, what you have is 1 over 2 to the n plus 1, e to the 0.1 over 2, which is which is 1 over 2 to the n plus 1, e to the 0.05. So there is a bound on the n plus first derivative that we can call m. And we use this now and say, we want 1 over 2 to the n plus 1, n plus 1 factorial times x0 for a Maclaurin polynomial is 0. And the biggest this can be is 0.1. If we require that to be less than 0.5 times 10 to the minus 4, that will give us what we need. I didn't put 1 for input. Oh yeah, 1. N should be 1 over 2 to the n plus 1, e to the 0.05. So I'll replace m with this. I'll pick x to be the biggest it can be, 0.1, and I'll put in and then I've got the n plus 1 factorial. There we go. So you just have to choose n to match that. And now this is pretty hard to figure out what n has to be exactly. But what you can, oh, I'm out of time, sorry. What you can do in practice is just try the first few n's. Try n equals 1, or try n equals 2. Then we got 1/4 e to the 0.05 over 3 factorial is 6 times 0.001. Well, guess what? This is a lot less than 5 times 10 to the minus 4. This is already 10 to the minus 3. This only has to be a half. N equals 2 works. So we can just take the first two terms. We simply take P2 of x equal f of 0 is 1 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial. That's the Maclaurin series for n equals 2. Go up to x squared. And so this is 1 plus 1/2 x plus 1/4 over 2 factorial x squared is, let's see, 1/8 x squared plus 1/2 x plus 1. So there's a polynomial, but you just try the first few n equals 1, maybe just make it smaller, but n equals 2 does, and you do that. All right, we're out of time, and I'm sorry I'm way over. The clock is fast. So, send me any questions you have. I hope that gives enough practice.
How many questions have you done the test?
I haven't written it yet. I'll try and make it a little short so you don't have to train too much.